Okay, guys, we're going to have a quick discussion on centroid of an area. I know I say quick discussion and then it turns out to be like a 12-minute video. But actually, this might just be longer because I'm going to do centroid of an area and then a quick example. Okay, so what we've seen thus far is that the way that we determine our centers of whether it's center of gravity, center of mass, or center of area, for example, is we say the moment of the total, let's call it gravity, the moment of the total weight is equal to the sum of the moments of all the weights. Okay, so the way that we determine our centers is the principle of moments. I really hope that that concept will stick with you. We're equating the moment of the total thing we're looking for with the sum of the moments. Okay, so what we saw is that x is equal to the integral of x dw, for example, over dw. That's just a moment equation. Where we got that from was x times dw is the integral of x dw, something like that. Okay, that's simply just a moment equation. We're saying that the moment of the total weight about a certain axis, there's the moment on, is equal to the sum, that's the integral, of the moments of all the differential weights. Okay, and the reason why we used integral is because we have a continuous system. We use the summation when we have individual discrete elements, discrete elements. Okay, I hope you're getting that idea, but nevertheless, it's the principle of moments. So we have this, and then we had y bar also is y tilde dw over dw. And what we saw was x, these x tilde and y tilde, is the location of the centroid. It's the centroid of the differential element. Okay? So these y tilde, x tilde is the centroid of the differential element. So if we got a differential, because remember, if we've got a continuous system, the first thing we need to do is we need to set up a differential element. We need to define our differential element. And we are taking moments about a certain axis. And so our x bar is that x tilde is the location of the differential element. And the y tilde is the location of the differential element in the y direction. But it's the location to the centroid of that element. Okay? Okay, so I hope that's clear. And the x bar and the y bar is the location of the centroid of the total area, of the total volume, of the total weight, of the total mass. So these are the total centroid location, and these are the location of the differential elements. Okay, so I hope my explanation is somewhat clear. So when we come to centroid of an area, what we have essentially is a two-dimensional area, okay, and it's given by a function. This top line here, whatever it is given by some function, okay, and we are trying to find the centroid. So what do we do first? Step one, we need a differential element, because it's the equation, the moment equation is given by this, x tilde dA divided by dA, the integral of dA. Remember? So it's the moment of the total area about a certain point is equal to the sum of the moments of all the sum of the differential areas. Okay? So the first step is we need a differential element. What we do is we set up a differential element like that. Remember when we had discrete particles, we added up those discrete particles. But when we have a continuous system, we don't have discrete particles anymore. We are adding up differential elements. And so we have to set up a differential area. The width is dx, the height is y. So our dA, our differential area, is then equal to the width times the height, or the height times the width, which is y dx. Okay? So let's move this here. So x bar is equal to x tilde times dA, which is y dx. Okay? Over y dx, because we have integral of dA at the bottom. So dA is y dx. What is dA? It's the area of the differential element. It's the area of the differential element. Okay? Now what is x tilde? So we've sorted that out. What is x tilde? X tilde, again, is the location of the centroid of the differential element. So I need to find, first of all, locate the centroid of your differential element. Because it's a rectangle, it'll be right there. Now I need to find what is x tilde. Well, in this case, it's just simply equal to x. So my x bar is then going to be x, because x tilde becomes x, times this, y dx, over y dx. But now we've got different variables, so now we need to replace this. But what was y? Y is just a function of x. So if y is equal to whatever, half x squared, for example, say now that was the function of this curve, then you would just put that into there, and it would become x times half x squared dx over y equals a half x squared dx. And then you would just solve the integral, and you would solve for x. Okay? So step one, find the differential element, or define it first. We've defined it. Number two, describe it. Describe the area. The area was height times width, y dx. Okay? And then the second step is the centroid, or rather the x tilde and the y tilde of the differential element. You need to determine what these are. In this case, x tilde equals x. Now, what about y bar? We know y bar is equal to the integral of y tilde times dA over dA. Now what is dA? We've already defined what is dA. It's equal to y dx. dA is just the area of the differential element. So y is the height times dx. We've got that. But now what is y tilde? Y tilde, again, is the location of the centroid of the differential element. So there is my y tilde. Okay, there's the centroid, and there's the location of that centroid. But what is it in this case? If I use this differential element, it is going to be y over 2, because y is the height, and this is half. So in this case, it's going to be y over 2. All right? So then I have y over 2 times y dx over y dx. Then I need to convert these into x, and I need to convert that into x. Okay. Let us look at a quick example. Okay, we're going to look at example 9.5. Look at example 9.5. Okay, so here we've got an area. We're trying to find the location of the centroid of the area. The centroid of the area is just simply if I find that point, I can put my finger under that point, and this whole area will balance. It will balance, okay? So how do I find it? First of all, I need to set up a differential element. There's my differential element. It looks very lovely. It's this element in the gray. That is my equation for to locate the centroid in the x direction and the centroid in the y direction. And it's x is equal to the integral of x dA over dA. Now, I've defined my element like this. By the way, you can define your element like that. But first step, let's define our element like this. So what do I need? I need, what is the area of that element? Because I'm looking for dA. What is the area? It's height times width. What's the height? In this case, it's simply y times d, and the width is dx. So the area of this element is y dx. Okay, it's the height times the width, y dx. Tick. Number one, we've done it. But now I need to find out what is the location of the centroid of that differential element. What is the x tilde? Sorry, okay, what is x tilde? It is simply going to be x, right? X tilde is simply going to be x. Okay? Then we substitute and we get x cubed and we get x squared and we solve the integral and we get 0.75 in the x direction. Okay? Does that kind of make sense though if you get 0.75? Can you see it's kind of increasing exponentially? Right? So it's increasing like this. So the centroid, the x location of the centroid, my gut feel says it should be this side, and it's true. It's 0.75, so it's towards that side. What about y bar? Y bar is equal to the integral of y tilde dA over the integral of dA. Now, what is dA? We've already determined what it is. It's the area of the element. But now, what is y tilde? Y tilde, again, is the location of the centroid of the differential element. And because the height, the total height is y, and the centroid is located at half that distance, it's going to be y over 2. Okay, that's what we get there. And you plug those in. Now, the important thing, which just to show you again, what you get here is x times y. So all you need to do is convert that y into x squared, because y equals x squared. Plug it in there, and you'll get that. In the bottom, y is actually equal to x squared. So you need to put that in there. Similarly here, where you have the y, you just put in the x squared, okay? And you solve it. The other way to do this is to have, you see, guys, if you've got this differential element like this, then what you're doing is you're summing from that side to that side. You're adding up all the differential areas as you move from there to there, okay? Because it's going from 0 to 1, right? 0 to 1. So we're summing up this differential element and we're going across like that. You can also choose a differential element that is horizontal, but then your dA, then your differential area, let me just wait for it to focus. Wow, if things are not in focus, it's not very helpful. Okay, so your differential area is then, again, your width times your height. Your height is dy, but in this case, that length of your differential element is not going to be that simple. It's going to be, in this case, it's going to be 1 minus x, because that total length there, the total length is 1. That length is x. That length there is x. And so that length of the element is going to be 1 minus x. So there's the length of the differential area, and there's the height is dy. So you see it's changed a little bit. Now what about the location of the centroid of the element? Well, we're looking for that point there. So it's going to be x plus that length divided by 2. So it's this length plus this length over 2 to get to there. So that's what we have there. X plus 1 minus x over 2. Okay. Then what about the y tilde? Y tilde is just simply going to be y. That's what we have there. Okay. And you plug all those in and you solve. Okay. So hopefully this has given you a basic idea of how to go about solving the area centroids. Okay. Cheers.